and we are ready for the last chunk of this lecture. Now we would like to discuss some complexity issues with Dixon's approach and similar approaches. So, first of all, we know that B, the size of B, can be small or can be large. What is better? Well, small b means that we have small vectors. So, small binary vectors. Vectors. And also the factorizations are fast, because we are looking only for these factors. And fast factorization. But then it's difficult to find the Ri such that Fri can be decomposed in that basis. So if B is small, there are very few integers which are smooth from B. So a large B gives the advantage that we have many numbers smooth from B. So when you have an actual version of the algorithm, you have to find a compromise, a trade-off between these two. On the other hand, this is B. What about U? Now, if you have B, as we saw, U comes from linear algebra. However, there is another approach. You can start from U without B. What it means? You factorize, and any factor you find, you add to the factor basis. So from U, you can get B. Now, this way, maybe anytime you compute, you find new factors, and B grows, and becomes infeasible. This way, it can be difficult to find enough numbers to get the linear relation. So these two strategies, you have to think what is better, depending on your situation. But if you take a very refined version of Dixon, you can get a nice complexity. So a refined version of Dixon can arrive to the following complexity. So the security parameter is the number of bits necessary to write n. So it's the logarithm base 2 of n. So our formula will be in this n. And the complexity here is something of the order of 2 to the square root of n times the square root of log n, which is basically 2 to the square root of n. Now, we can have another version of a modification of Dixon, which is called the quadratic sieve. And the complexity is the same asymptotically, but it changes in practice cases. So asymptotically they have the same complexity, but in practice sometimes one is better, sometimes the other is better. The quadratic sieve is exactly like Dixon. The only difference is f. F of Ri, if you remember, f of x is simply x squared minus n. And then you reduce modulo, it's a square modulo minus n. Now what happened? What happened is that, of course, f of x is congruent to a square minus n modulo n. x squared. So x squared is congruent to fx, which is square minus n, and of course, so we have simultaneously two conditions. X squared is different from x squared minus n. So we can take any r. Any ri is okay. We don't have to check that ri is greater than the square root of n. However, then again we have to compute the greatest common divisor. We do everything, and what happens? Maybe we don't find it. So depending on the situation, you can use Dixon or quadratic sieve. They are very similar and they have the same asymptotic complexity. However, there are better ways to do these computations. The best algorithm known as today is the general number field sieve, which uses Dixon's idea, Fermat's idea, but the computations are not made over Z, but in larger fields. So we have larger fields, complex mathematics, complex algebra, and so we are not going to detail this method. It's too much for this course. But the complexity of this method is 2 to the cubic of n, and then log n squared, which is basically 2 to the square root of n, to the cubic root of n, where n is the usual one, where n is in this way. So, what is the complexity of the brute force approach? Try every possible factor up to the square root of n. So brute force cost, you try all factors of n, all numbers up to square root of n. And this is 2 to the n square, so 2 to the n over 2. Therefore, brute force is exponential in n, but the sieve is sub-exponential, is much, much better. Now, we have done some computations, also in practice, how many operations we need, how many flops we need on a computer. And we found the following. If you want to break n of the order 2 to 768, all you need to do is to find 1 million euro, buy cluster of computer, and then you can break 1 key every 6 months. 1 key every 6 months. So keys, RSA keys which have this length, and there are some of them still around in some smart cards. They are not really secure unless they protect values, unless they protect some secrets that have very low values. Nobody will spend 1 million euro to get my bankomat, for example. But other bankomats may be interesting. If we pass to keys 1000 bit long, then the cost is 1 billion euros, and you need many years to break 1 key. So keys with this length are still secure. However, everything that I said until now, the complexity estimates are for the generic case. The estimates, the complexity are for random keys. So if the two primes are computed randomly, are obtained randomly somehow. Next lecture we discuss what is random, and the random that we need for cryptography. Now I'll tell you only that there are weak keys that can be broken very easily even if they are long. Keys which are long 1000 bits, they can be broken in a few seconds. And we've done it in our laboratory, it's very easy. Weak keys, there are many kinds of weak keys. Just to give you some examples, if P and Q are very close, is a weak key. And then if P minus Y is move, is Y is move with Y small. And then also you have to be careful on E and the messages, because it can be that M to E is smaller than N. This is dangerous too. However, any family of weak keys has its own special algorithm to factorize it. And we see all these algorithms in lecture 9.